Hello grade 12s, good to be with you. Today we are going to be looking at a chemistry topic, that of acids and bases. Now this is a very interesting topic. You might have come across some of the terminology in grade 11. We're going to expand it quite a lot in this grade 12 Learn Extra lesson. So let's go and have a look and see what acids and bases are all about. Here we go. In this lesson, we'll focus on the following things. We'll start by revising the idea of an acid-base model. There are different models to explain the nature of substances as being either acidic or basic. We want to know those and make sure that we've got that as the concrete basis for our discussion on acids and bases. Then we'll be looking at comparing different acids and bases. We'll also define and calculate the pH of solutions. Now, pH is something that we haven't done in too much detail previously. We're going to be doing a lot more on pH to not only recognize that it's a scale to measure and to classify, but to actually calculate as well. We'll be able to do that by the end of the session. We'll also explain the process of a titration. This is an analytical technique that is used by chemists to calculate unknown concentrations of different substances. And for that, we're going to need to be able to do some calculations, which is exactly what that is, the last point of that. So guys, hold on. We're going to be first of all starting by doing some overview of some of the theory, and then we'll get into some example questions. Hopefully you can follow along with us and make sure that you're up to date as you watch this particular lesson. So where do we start? Let's start by looking at the models of acids and bases. Now there are two main models. The one that is most popular and most currently used is the Bronsted-Lowry base, or the Lowry-Bronstead model. And what does that basically tell us? Well, let's start with this and let's focus on it. We'll talk about the other model a little later. So what they reckon, Lowry and Bronsted, is if you have a substance which is an acid, then it could be something that is written like this. As an example, we'll take hydrogen chloride, and let's say that it undergoes a reaction. It's going to be added to water. Hydrogen chloride as a gas is added to water, and this will illustrate exactly what we mean by an acid. So when it dissolves, it forms the following substance. It forms H3O plus Cl minus. Now, in this particular example, I want you to take very careful note of what happens to the hydrogen chloride molecule. I'm going to circle it and underline exactly what we're talking about here. So have a look at what's happened to that. Well, the one thing that we can see clearly is that we've got a Cl minus left over. The other thing that we should recognize and should notice is that this substance here, the H, has left behind its negative electron, and it has attached itself to become a hydronium ion, H3O plus. It's attached itself to the water, changed the water to become an H3O plus. Take a look here, we had H2O, now we've got H3O, but we've got an extra positive. So what's actually happened here is that the hydrogen chloride molecule, which is a gaseous molecule at room temperature, it has donated a, let's just write that again. It has donated a hydrogen ion. Now, you should all remember that hydrogen is the first element on the periodic table. It has one proton and one electron. So if we look at the hydrogen ion, then what we're going to say, this is a hydrogen atom, one proton, and I'm going to draw one electron. Now there, it's got one proton and 1 electron. Now, what we're saying in this case, the hydrogen ion is going to be represented not by like that, but by H+. In other words, it has left behind its electron. Notice we saw that over there. And it's on its own. It's just H+. So what is the H+? If it's a lost 1 electron, if it's no longer got the electron, and it's just that, then we could think of it as being a proton. And so when Lowry and Bronsted looked at this and began to understand, thinking about what's happening in an acidic solution, they said, well, you know what, we think a really good definition of an acid would be something that donates a proton. Donates a proton. In other words, an acid is a proton donor. An acid is a proton donor. But then what is a base? Well, in this very simple equation that I've shown, it also illustrates exactly what a base is, according to the definition of Bronsted and Lowry. Because what was the substance that accepted this proton? Well, there it is, water. What happened to the water? It changed to this H3O plus molecule. It has gained a proton. It went from H2O to H3O, and because it has more protons than electrons now, we've said it's a plus on it. So the water molecule here has changed. The water, what happened to the water? It accepted a proton. So we could say this is a proton acceptor. And by definition, we say that therefore it is a base. Now, we can look at numerous and lots of different reactions with acids and bases, and you'll be able to see that every time that we've got something that is basic, it accepts protons. Every time something donates protons, that's a source of hydrogen ions, then it will be acidic, according to this particular definition. And we can use it widely. Really is a very useful definition, very useful to understand that these reactions happen in partnership with each other. That there is usually a pairing. Something is an acid and something is a base, and when you combine them, there's an acid-base reaction. So bear that in mind. Now, what about the other model for describing acids and bases? This is an older model, was developed by a man called Arrhenius, and the Arrhenius model is slightly different, and it is a little less, it's a little more limited, because what Arrhenius said is if a substance liberates, liberates or produces hydrogen ions, H+ ions, then it's an acid. And if a substance produces OH- ions, then it is a base. Then we have a base. Okay? Now, this doesn't hold in all cases. There are some substances that don't produce hydroxide ions, but they will still be proton acceptors. They will still accept protons, and therefore, in the definition of the Bronsted-Lowry theory, we would say that they are actually bases. Let's show you one particular one that might explain that quite well. And we're going to take something like ammonia, and if we add it to water, if we add it to hydrochloric acid at least, let's do that, then what we will get take those two gases, combine them, then you will get this substance, ammonium chloride. Let's not use water. Now, look exactly what's happened. The hydrogen has moved onto there to form NH4. What has happened to the chloride? It stayed on its own. We could split that out. So what's ammonia doing in this particular case? Ammonia is accepting hydrogen plus, hydrogen ions. There's no formation of H plus. There's no formation of OH minus. But what we're seeing is this ammonia molecule is accepting hydrogen ions. The HCl is donating. So in terms of Bronsted-Lowry, this is an acid-base reaction. In terms of Arrhenius, he's saying, but I don't see any hydroxide ions being formed. It's true, there are no hydroxide ions being formed, but still the ammonia is acting as a base. So that's where we get these scientific models. They don't explain everything sometimes, and that's why we have two theories to put them together. As I said to you earlier, the Bronsted-Lowry theory model is more common, it's more updated. But there are many other models of acids and bases. These are the two that you may be asked to explain and define acids and base behavior in terms of these models. Let's move on. Having got that definition of what is an acid and what is a base, and let's have a look at some classification of acids and bases. Now, relating to the Bronsted-Lowry model, the one thing that you need to recognize is that these are pairs. They are often found in the same reaction, as we've illustrated earlier. So we get a pairing of reactions. So let's take a look at the same reaction that we had earlier, simply hydrogen chloride and water. This is one of the easiest ones to look at. And we're going to say that produces chloride ions, and we're going to have hydronium ions, H3O+. I should really say, even if that's a gas, that's a liquid, that's in aqueous solution, and that's in aqueous solution. Now, we've already clearly said we can identify that this is an acid. We can identify that let me use a different color because I want to illustrate something very clearly, that this is a base. Why? Because the acid donates protons, the base accepts protons. But now, the very interesting thing is in many acid-base reactions, they are not just straightforward reactions, but they're actually systems in chemical equilibrium. And so there's not just a forward reaction, but a reverse reaction as well, a forward and a back reaction. So if we were looking at the back reaction now, let's classify according to Bronsted-Lowry what's actually happening. So if we had to look at this substance here, and I'm going to use a different color, the H3O+. What is different about the H3O+ compared to the water? Well, the H3O+ has got an extra hydrogen ion. So this particular substance, if I'm using the back reaction, H3O+ goes to form H2O. What's happened to it? It has donated a hydrogen ion. So this is in the reverse reaction is behaving like an acid. So what we would recognize is it is paired to the original base. It's in a pair, but we call this the conjugate acid. So these work together in a pair, the base and its conjugate acid. It's an acid because it's donating in the reverse reaction. It's conjugate because it's paired to the original base. So we recognize the base and its conjugate acid are water, and H3O+, hydronium ion. Please be very careful that you identify the base and its conjugate acid. It's not a random pairing. The base and its conjugate acid are the same things. They only differ by 1 hydrogen or 2 hydrogen ions. So be very clear about that. So could we say the same about the HCl? Well, in the reverse reaction, what's going to happen to this chloride ion? I hope you can see that it's going to accept a hydrogen ion from the hydronium ion to form hydrochloric acid, or hydrogen chloride. This whole thing is called hydrochloric acid solution, but it will form hydrogen chloride molecules. So let's be very clear about it. What is this doing? It's behaving like a base because it's accepting a hydrogen ion. What sort of base is it? Is it an ordinary base? No, it's in the reverse reaction. It is paired with something that was an acid, so it's the conjugate. Conjugate is just meaning a pair. It's coupled. Notice it's only different. Cl minus and HCl only differ by 1 H, 1 hydrogen ion, 1 proton. That's what makes them different. So there's my second pair, the acid and its conjugate base, hydrogen chloride, and chloride as the ion. Not chlorine, it's an ion. Chloride is the ion. Now, guys, we can do lots of these acid-base reactions, lots of these pairings. It's very important that you understand that there could be, there are always 2 pairs in an acid-base reaction. But very clearly and very important about these particular reactions, I've chosen this particular acid, HCl, because it donates 1. So it donates 1 hydrogen ion. And we call this monoprotic. But if it were to be something different, say something like H2SO4, now that can become SO4 2 minus. Then it's going to donate how many? It's going to donate, it donates 2 H plus. And if it donates 2 H plus, we call it diprotic. And obviously, if it was something like this, H3PO4, then it could donate, just put the arrow in for me, it could donate 3 hydrogens. And if it donates 3 hydrogens, then we're going to get PO4 3 minus plus 3 hydrogens. So we'd call that triprotic. Now, very important for you to recognize, in all this process, we're donating hydrogen ions or protons. The word protic means a donation of proton. It comes from proton. Protic, so you get monoprotic, diprotic, triprotic, even polyprotic. Poly meaning many. Okay, so I hope you've got that very clearly, that terminology clearly wrapped up in your head, and you're understanding that and making sure. There's one other little word that I want to talk about, and that all of these reactions where it's involving the donation of hydrogen ions or protons, we sometimes call protolysis. Protolysis means a donation of H plus ions, hydrogen ions. Okay, so be very clear about the terminology. There is terminology you need to know and you need to be able to explain and understand, and it's very important that you see as well when we come to calculations. Ask yourself, are we dealing with a monoprotic, a diprotic, or a triprotic acid? Or, in fact, we could be dealing with something that is a base able to accept, in the conjugate sense, more than 1 hydrogen ion. Okay, so be very clear about that. Let's move on to another interesting idea. We've spoken about acids accepting hydrogen ions. We've spoken about, acids donating hydrogen ions, bases accepting them. But what about substances, and there are many of them, that can do either? They can accept or they can donate. And there are some classic ones. We're going to look at water as an example. These substances can react as either an acid or as a base, and they are called amphiprotic. Amphi meaning both ways. So like amphibian can be alive in water as well as on land. Amphiprotic can be an acid or a base. So they're also known as ampholites. So let's have a look as the example of water, just to remind you. Take a look here. We start with water, and it breaks apart to form a hydrogen ion, where it's donated its hydrogen ion, it's formed that hydrogen ion. What's left behind? The hydroxide. Now, look at the hydroxide. In the reverse reaction, what's the hydroxide doing? It's accepting the hydrogen ion. So in this case, what we've got is the reverse reaction. That hydroxide would be the conjugate base. This will be the acid because it's going to donate it to form the water. So there's a donation of, this is a proton donor. Proton donor. Very clear. What about this reaction now? If we have water and we add a hydrogen ion, what are we going to get? We're going to get this hydronium ion. What's water doing? It's accepting a hydrogen ion, so it is acting as a base. Base is a hydrogen ion acceptor, proton acceptor. Okay, so we've clarified some terminology. Let's move on to classify different types of acids and bases. Before we get there, let's just spend a few minutes on the protolysis of water, because this is incredibly important. And I need you to concentrate here, because really all that we've done up until the moment is a little bit of a recap, and maybe you've heard it before. But this section that I'm going to deal with now, this concept, is extremely important, because it will take us through the foundation of defining the pH scale. We'll come back to that as a key concept. So where we're looking now, we're beginning to see that we could have water as a liquid molecule, water, another molecule of water as a liquid. It will form hydronium ions and hydroxide ions. Notice what's happened. Water is amphoteric. It has, in this case, accepted to form the hydronium ion, and in this case, it has donated to form the hydroxide ion. So there is a process. Notice it's also in chemical equilibrium. So if we wanted to, remind yourself, in a closed system, a solution of water at a fixed temperature, let's take 25 degrees Celsius, we could say this is a chemical equilibrium. There are hydrogen ions, hydronium ions, and hydroxide ions, and there are molecules of water in a glass of water. So even in this glass of water, at room temperature, there are a combination of molecules and water. Molecules of water and ions, hydrogen ions, and hydroxide ions. But because it's in chemical equilibrium, we can therefore say that we can write the equilibrium constant expression for this particular reaction. Now, because it's water, we write it as Kw, and we're going to say to ourselves, what do? We take the concentration of the hydronium ions, or hydrogen ion, because it's the product, multiplied by the concentration of the hydroxide ions, and divide it by the concentration of H2O times concentration of H2O. But you'll say to me, hold on. When we did chemical equilibrium, we took very careful note that we don't need to include the liquids or the solids because their concentration doesn't change. So I can simplify this particular equilibrium expression because the hydrogen, the concentration of the water, that's going to be a constant. It's not going to change. So what I'm going to do is I'm going to simplify the Kw expression and simply say Kw is the hydrogen ion concentration times the hydroxide ion concentration. I hope that's clear. Make sure that you've got that. And now the next step that we need to understand, that people have measured that particular Kw value, sometimes called the ionization constant of water. Sometimes it is known as just the Kw. It's the equilibrium expression for water. And what we're going to say is that is 1 times 10 to the minus 14. This is at 25 degrees Celsius. So remember, the Kw is temperature dependent and it is sensitive. The next thing that you need to understand is that in a solution of water, back to the equation, what we'd recognize is that the number of moles of hydronium is equal to the number of moles of hydroxide. So these two are equal. So what we can say is the concentration of H3O plus is equal to the concentration of OH minus. Okay, recognize for every one hydroxide ion, we're going to have a hydronium ion. And in the same way, we can put those together. So that means that therefore we can say the concentration of the hydronium ion in a sample of water is going to not be just this, 1 times 10 to the minus 14, but is going to be the square root of that. Because if those two are equal, we can square root, and we get 1 times 10 to the minus 7. In the same way, we can say the OH minus ion concentration is 1 times 10 to the minus 7. Check it out. If you take 1 times 10 to the minus 7 times 1 times 10 to the minus 7, the bases are the same, 10, and you can add the exponents. Minus 7 plus minus 7 is minus 14. So that's a really critical and important fact. We're going to come back to that very shortly. So please take note that when we're dealing with the protolysis of water, this is a fundamental idea. Only for water, there is a Kw value, and it's a set value. This is the building block on which we will build our pH scale. Maybe some of you can start to get an inkling of what the pH scale is all about as you look at those two values and recognize that in water that you've got this situation where they're equal to each other. The hydrogen ion concentration and the hydroxide ion concentration are equal. Very, very important. This isn't always true. When we've got acids, we don't have an equal concentration of hydroxide and hydronium. The equilibrium is shifted. That's very important to establish, to make sure you understand that. And so our next idea is just dealing with this application of classifying some acids and bases, bearing in mind that in most cases we've got an equilibrium reaction. So when we talk about strong acids, we're talking about a solution in which we've got a high concentration of H+. Okay? This concentration is high. What we say, like in the one that I showed you earlier, HCl plus H2O gives you H3O plus Cl minus. It is a reversible reaction, but what we're recognizing here is that this equilibrium is shifted in such a way that it is mainly favoring to the right, that this is very high. In fact, there are very few molecules. There's a minority. This is small concentration. We say strong acids ionize almost completely. The stronger they are, the more they will ionize. And so in this solution of water now, you've got a predominance of H+, which means that you're going to have many, many more H pluses. We started with water, equal number of H plus and OH minus. We've now added H plus, so all of those OH minuses have changed. Many of them have become H plus. Very few of them remain as OH minus. So the concentration of the hydroxide ion is low, the concentration of the hydrogen ion is high. Very, very important. We therefore will say that the Ka value, now the Ka value is going to be the product of the hydrogen ion times the hydroxide ion concentration, or in this particular case, sorry, it's not that. It's according to the reaction that we've got. The Ka value here is going to be a higher value. So the Ka is high. Okay? The Ka is telling us the hydrogen ion concentration is high. It's not going to be a small value. When we talk about weak acids, then the opposite happens. Weak acids, we get incomplete ionization. So, for example, if we take vinegar, which is this substance here, and we add it to water, then we will get that forming. Now, if we look at the Kw or the Ka of this, what you'll need to recognize is that this will be in aqueous solution, even though it's a molecule. This is a liquid, and this is aqueous. This one is aqueous. But what's going to happen is that if you look at the Ka here, you've got the concentration of the ethanoic acid or vinegar molecule is going to be high. The concentration of this one isn't going to be so high, and this one, the hydronium ion, is also not going to be so high. So if you look at this, this is going to give you a small, it's going to give you a small Ka, because it hasn't ionized completely. The molecule is going to be in predominance. The molecule of vinegar, the acetic acid molecule, there's going to be much more of that. Notice that's on the denominator. So the concentration of this is going to be high. It's going to be a big denominator. If you divide by a big number into even a small number, you're going to get an even smaller number. So weak acids don't ionize completely. They have a small Ka value. And you need to understand where those terms are coming from. In a similar way, we can say a strong base. It will dissociate completely. And when we're talking about the reaction, the equilibrium reaction of a base dissociating to form its particular substances, something like sodium hydroxide will form the sodium ion plus the hydroxide ion. Now, this substance, this all happens in solution. It's in an equilibrium situation, but the majority of it is dissolved. It's an aqueous solution, and there's very little of that. So strong bases have a large value. They have a large Kb, large. But weak bases do not dissociate completely, so they have a small Kb, because incomplete dissociation. So guys, please bear this in mind, that when you're given data, you're given information about Ka and Kb, Kw, they're just the equilibrium expressions for a reaction. What we're saying here is the difference between acids and bases. We've defined those. We've recognized that acids are proton donors, bases are proton acceptors. When we've got a base, it can either be weak or strong. An acid can be weak or strong. But please don't get those mixed up. Make sure you understand the difference between weak and strong. It's all about the formation of the hydrogen ions in the solution. There's another thing that examiners love to ask in terms of classifying the strength of acids, and learners often get it mixed up. We talk about strong and weak acids. Remember, a strong acid will always be a strong acid. It doesn't matter where you've put it, what you reacted with, it will always be a strong acid. So the strong acids that we commonly deal with: hydrochloric acid, nitric acid, and sulfuric acid. Weak acids, anything else really that is an organic acid, it's a weak acid. You've come across them. Something like sulfurous acid or hydrogen sulfide forms a weak acid. Bases, the bases are very interesting because strong bases are also known as alkalis. Alkalis are strong bases that dissolve completely in water. So the strong alkalis are known as lithium hydroxide, sodium hydroxide, potassium hydroxide. They have very high Kb values relatively to the others. If we take something like calcium hydroxide, its Kb is quite low. We need to understand that. Remember, it doesn't dissociate completely, doesn't separate into its ions completely. Now, bear that in mind, and there's one last term that I need to pass to you. We're going to do an exercise with it, but I just want to mention it here. The strength or weakness of an acid has nothing to do with the fact whether it is concentrated or dilute. Concentrated, concentration, remember, tells us the number of moles per volume. So if I've got a large number of moles in a small volume, then it will be concentrated. But if I've got a small number of moles, if this is small, in the same sort of volume, in a large volume of solution, then the concentration is going to be weak. I've got not weak, it's going to be dilute. It's we've added more water to it. It's far apart. The molecules, the ions are far apart from each other. They're not as many. It could still be a strong dilute acid or a weak concentrated acid. Please make sure you've got that difference. Now, I've been promising you a look at the pH scale, and let's get into it right now, because this is very, very important and very critical for your understanding. So I'm going to start with the definition, and then we're going to see where it comes from. The pH is a special maths function, and it's defined simply like this. The pH is equal to the negative log, which is to the base 10, of the hydrogen ion concentration. We've written it as hydronium ion there, but you can write it in the same way as negative log of the hydrogen ion concentration. Okay, so what does that mean? If we've got the concentration of hydrogen ions, then we can take the negative log. I don't want to give you a maths lesson here, but remember we said earlier, in water, the hydrogen ion concentration is equal to 1 times 10 to the minus 7. So when we take the log, what we're asking for is what is the power to the base 10? What is the power? And now they've said negative log. So we're going to take the power, which was minus 7 there, multiplied by a negative number, and we're going to get out a value of 7. That's the input. That's exactly what we're doing. I just want you to see. So from this, we can do it without even a calculator. We can say, let's apply the log idea. Log says, look at the exponent. What's the exponent? Multiply the exponent by the negative, and then you'll get the pH. And so what we're saying is there, it's the negative 7 multiplied by negative gives us 7. So the pH of water, where the concentration of the hydrogen ion and the hydroxide ion are equal, is 7. Got it? Hope you got it. Now, we could say in the same way that there is another definition. We could say pOH. And we define the pOH as negative log. When we write it as log like that, we're writing to the base 10 of the hydroxide ion concentration. So the pOH, in the same way, is equal to 7. We can put those two statements together, and we can get this very useful idea that the pOH plus the pH is equal to 14. When mathematicians and chemists looked at this, what they're saying is, we've got a big range of concentrations. 10 to the minus 14 is a very, very, very small. We want to collapse that scale, make it a little bit shorter. Counting from 0 to 14, it's fine. Counting to millions and millions and millions, 10 to the minus 14 millionths, we don't like doing that. We don't like working with those very, very, very small numbers. Even times 10 to the minus 7, it's 10 billionth. Not nice to work with all those zeros. So let's put it on a logarithmic scale. We collapse it, make it shorter. But here we get the interesting idea now of the relationship between pH and the hydroxide ion concentration. So if we recognize that these two will always add up to 14, then we're going to be in a very interesting situation. Notice that 10 to the minus 0 is going to have a pH of 0. 10 to the minus 1 will have a pH of 1. 10 to the minus 7, we've just seen, has a pH of 7. 10 to the minus 14 will have a pH of 14. Remember, the bigger the negative is, like minus 14, it's actually very, very small. So this is saying we haven't got many hydrogen ions. It's telling us, with this relationship in mind, that we've got far more hydroxide ions present. Now, on the scale, they've defined for us anything where the hydroxide ion concentration and the hydrogen ion concentration are equal, that's going to be 7. But if we disturb that equilibrium in water by adding acids to it or acid-type molecules to it, dissolving hydrogen chloride, then it's going to shift the equilibrium and we're going to get things that are acidic. In the same way, to a solution of water, we add sodium hydroxide. We're going to make it more basic. The hydroxide ions are going to increase and the hydrogen ions are going to decrease. There's always going to be that product. Go back to it. The Kw is always going to be H plus times OH minus is going to be set. It's going to be equal to 1 times 10 to the minus 14. We can increase the one, then we must decrease the other. Hope you've got that very clear. Make sure that you understand this pH scale. We're going to use it to do some calculations in a little while. Now, when we do an acid adding to a base. We call that process neutralization. And we do this in titrations. It's a very useful analytical technique, so we can tell what an unknown concentration of stuff is. So we've got a known concentration of an acid, and we've got an unknown concentration of a base. We can add the acid to the base and find where they neutralize. How are we going to know when they neutralize? Well, there's some very clever chemicals that we can use, which are known as indicators. They will change color dependent on the concentration of the hydrogen ions. So if we're adding a strong acid and a strong base, we neutralize them exactly. The end result will be there will be water present. At that end point, or equivalence point, the color of the indicator should change, and we know that we've exactly neutralized the acid and base. So if we were adding sodium chloride and hydrochloric acid, we would get an acid plus a base gives us salt plus water. We would have no excess acid and no excess base. We would only have salt and water, and the pH of water is neutral. So if we got an indicator that changed at that neutral point, we'd be able to work out so many moles of acid, so many moles of base have been added to each other, work it out in ratio, calculate the unknown. And that's exactly the steps of neutralization. I'm not going to go through this in too much detail. I've explained it. The end point where exactly every hydrogen ion has been neutralized by a hydroxide ion is where the indicator changes color, and we call that the equivalence point, where they're exactly colored. Now, if you use the wrong indicator, you'll have an end point, but it won't be the equivalence point. So be very clear about that as well. So the equivalence point is indicated by the color change of a suitable indicator. And so what indicators should we use? Well, there are a range of indicators. You don't need to necessarily learn different indicators, but it's a good idea to have in your head that some indicators are suitable for certain acid-base reactions and some are not suitable, are better suited for others. So the choice of indicator is very important. If we have a strong acid and a strong base, now remember, strong and strong, that means that there is a high concentration of hydrogen ions for the strong acid, a high concentration of hydroxide ions for the strong base. The indicator that you will use is bromothymol blue or methyl orange. You'll get a very sharp change in color, and you'll be able to determine that. The range of change, or the points of change, will be in the pH range around between 4 and 7, but closer to 7 than 4. Now, if you use a strong acid and a weak base, then you must use methyl orange. The range of change is from 3,5 to 6,5. You'll notice that the acid is more dominant. It's closer to the acid side. The acids have the lower pH numbers. The bases have the higher pH numbers. Now, if you use a strong base and a weak acid, the range of the pH is going to be above 7. That's where the indicator is going to change. And you're going to see that the best indicator for that is phenolphthalein. Now, in a question, you'll be told what those color changes are, and you'll be able to select the correct ones. Please make sure, if you're doing this practically, that you understand and look out for the correct color changes. Very careful. One drop of the addition of the acid or the base will change the indicator, and you need to work carefully with that. It's a very important technique. Okay, now we've covered a lot of theory so far, and I think it's about time that we took a little break. When we come back, we'll be looking at some questions where we can apply our knowledge. So I'll see you after the break. Welcome back, Grade 12s. I hope you enjoyed your little break. I hope that you've consolidated your knowledge on acids and bases. We're now going to do some example questions that are typical of the type of things that you could expect in an exam or a test coming up. So my advice to you is make sure that you work through these questions on your own and check them. For these Learn Extra lessons, get the notes, do them before you're watching the DVD. Make sure that you're getting the right answers. If you don't get the right answer, please make sure that you copy down the correct solution, and then you can see where you've gone wrong. So let's get straight into it without too much further ado. And the first example question that we're going to is the following. It says, explain the following terms and give an example in each case. So there are two parts. We need to explain and we need to give an example. So a concentrated strong acid. Now, for lack of space, I'm going to give the example first of all, and that will help us explain it. So we're going to say a 5 mole per decimeter cubed solution of hydrochloric acid. Okay, so what does it mean? Concentrated strong acid means an acid that ionizes completely. That's the strong bit. The second bit is that has a large number of moles per decimeter cubed, or volume decimeter cubed of solution. So that's where the 5 mole per decimeter comes in. It's telling us there are, for every liter, there are 5 moles of HCl dissolved in the solution. So if we've got a liter, there are going to be 5 moles. If we've got 2 liters, there are going to be 10 moles. If we've half a liter, 2.5 moles. But it's a big number of moles. Remember, a mole is 6 times 10 to the 23 molecules of those hydrogen ion molecules. It's a huge number. So we need to be very careful of recognizing that what we're saying here, it's a strong acid because all of the acid molecules, the HCl, they're not going to stick around as HCl molecules. They're going to break up into hydrogen ions and chloride ions. So the concentration, we can say, looking at the equation, is 1 for 1. For every 1 molecule of HCl, we're going to produce 1 molecule of hydrogen ion, hydronium ion, and so that's what it is. It could have been sulfuric acid, or it could have been nitric acid. Those are the strong acids. High concentration, anything above 2 mole per decimeter cubed, 2 molar, is considered highly concentrated. Now, we need to look at the next one. What about a dilute strong acid? Well, let's just take 0.1 mole per decimeter cubed. And again, we'll choose one of the same ones that we've said of nitric acid. And the reasoning is the same. Here we've got a small number of moles in the solution, but it ionizes completely. Okay, I hope you can start to see the difference between these two. All that we're changing is the concentration. Both these cases, we could have used those other examples, used the same example. Now, compare these next two. We talk about a concentrated weak acid. Let's choose our weak acid as being ethanoic acid. Confident about that. Get your examples clear. So even if it's dilute or it's concentrated, we're going to use ethanoic acid. We've identified that as ethanoic acid because it does not ionize completely. In the solution, there is going to be some ethanoic acid molecules. The Ka, remember, is going to be low. Okay, it's not going to be a high Ka, it's going to be a low Ka. The number of hydrogen ions isn't so big, and the number of molecules of ethanoic acid are going to be big, so the Ka is going to be low here. So bear that in mind. Concentrated, well, let's just say, let's make it 2 mole per decimeter cubed of acetic acid. It does not ionize completely. That's why it's weak. Well, we could use the same argument here, but simply do 0.1 mole per decimeter cubed, because now that's diluted. Okay? Diluted means we've added more water, we've got less moles to the volume of solution. Now, the next one, we're going to talk about the base. Concentrated strong base. Well, your strong bases are sodium hydroxide, potassium hydroxide, and to a certain extent you could say lithium hydroxide. These two are the ones that we would prefer. That one is not so common. So I would choose any of those two, and if it was concentrated, 2 mole per decimeter cubed would be sufficient, or bigger. What we're saying is these dissociate. Because they're ionic in nature, they split up into their ions, and the word that we use there is dissociate. Whereas the acids tend to be covalent in their nature, and they form ions for the first time. That's why we use ionization. Right, I think we've covered that one in enough detail. You go back and check your theory and make sure you can answer all these. And obviously add some more examples. Make sure that you can follow that. Also take a look and see if you can analyze and say, if I'm given this substance, is it a strong acid? Is it a weak acid? Is it a strong base? Is it a weak base? Is it concentrated or dilute, using the same rules that I've shown you? Now, what about the next example? Let's have a careful look at it. Tells us that concentrated nitric acid is diluted. Now, concentrated nitric acid, that means there's a high number of moles. Nitric acid, remember, is a strong acid. Nothing we do to it will stop it from being a strong acid. It is a strong acid, will always be a strong acid. It produces lots of hydrogen ions. But we're going to dilute it to form a solution of 0.1 mole per decimeter cubed. So we're taking it from however many moles we had in the original solution. We just told that it's very concentrated, and you can get pure liquid nitric acid. We can break it down, put a little bit of dilute it by adding acid to water or water to acid. Which one do you think? You need to know this. You need to be very careful that we never add water to acid. We always add acid to water. And the reason for that is that sulfuric acid can burst out of the test tube and it can burn you. So make sure that you've got it very clearly. You trickle the acid down into the water. We don't do it the other way around. So making very clear about that, we're asked to do the following. Write down an equation for this dilution. So here's my equation. Nitric acid, HNO3, plus water, H2O, is going to form H3O plus NO3 minus. Very simple. We recognize that that is in equilibrium. And now the next thing that they're asking you to do is you've written down the equation and identified the acid and its conjugate base. Now, be very clear. What is the acid? You've got on the left-hand side, you've got two substances. You've got water and you've got your nitric acid, the HNO3 molecule. Which one is acting as an acid? Remember what we said. An acid will donate a hydrogen ion. We want the acid and its conjugate base, the one that is like it. So I'm going to say to you, by looking at this, I see that the water has done what? It has accepted a hydrogen ion because the water has become H3O plus. So that means that this must be the acid. So this is the acid. We were told it's nitric acid, so that makes sense. But now what is its conjugate base? Is the water the conjugate base? No, the water is the base in this reaction. It's not conjugate. It's not of the same chemical formula. Remember what we said? We said the acid and its conjugate base will be the same substance. They'll only differ by a hydrogen ion. So we're going to look at for something that's got NO3 without a hydrogen ion. Ah, there we go. That's the NO3 bit there. So this must be the conjugate base. Now, let's see if it makes sense. In the reverse reaction, what is this NO3 doing? NO3 minus doing? Well, it's going to accept a hydrogen ion from there to go back to form that thing there. So it's going to accept. Accepting means it's a base. Conjugate means that it's paired with that acid. So the acid, let's write it, the acid is nitric acid, HNO3. Nitric, that's an N, nitric acid. And the conjugate base is going to be NO3 minus, which is the nitrate ion. Okay, so please make sure you've got this pairing of acid and conjugate base very clear, because this is very important in terms of your theory, understanding of the theory. So let's move on. The next couple of questions we're going to do all involve some calculations. Please don't get excited, don't run away, don't cover up your eyes and say, I can't do it. They are straightforward. We've chosen a couple that are a little bit, that follow the general trend. So they'll each be different, but they all have important things for you to take note of. As you watch these examples and you work through them yourself, you can do others that are similar to this. And no doubt, you'll find some like this will come up in your exams or tests. So let's read it and make sure we've got all the information we require. It says an amount of 12,3 centimeters cubed of 0,0 mole per decimeter cubed solution of sulfuric acid neutralizes, there's the key word, 36,9 centimeters cubed of sodium hydroxide solution in a titration experiment. So we are dealing with titrations. Very important for us to recognize. We've got an acid plus a base. Now, what we need to do is we need to read the rest of the question before we get too excited about this type of question. It says, what indicator would you use would you use this in this reaction? Explain your answer. So have a very clear sense here. What do we know about indicators? We need to know what type of acid and what type of base we're dealing with. If we're dealing with a strong acid and a strong base, then we need to use an indicator that's going to have an equivalence point, an end point, around about 7, as close to 7 as possible. Now, what do we know about sulfuric acid? It's a strong acid. I'm going to write SA. What do we know about sodium hydroxide? It's a strong base. So when we have a strong acid and a strong base, we're going to use something like bromothiamyl blue, or methyl orange, or screen methyl orange, an indicator that has an end point, an equivalence point, a color change in the range around about 7. So it must, the reason we're choosing this one, there's a color change in the pH range where neutralization takes place, where neutralization occurs. Remember, this is about pH 7. We're talking about neutralization here, where every acid molecule reacts with, as being reacted with a base molecule, and they've cancelled each other out. So we've got an equal number of acid hydrogen ions and hydroxide ions, an equal number. In the acid, remember that there are millions and millions of hydrogen ions. In the base, strong base, we've got millions and millions of hydroxide ions. Neutralization, we want to pair them together so we've got the same number of each substance so that they cancel each other out and they form water and a salt. Now, we'll see this when we write the balanced equation, which is the next question. It says write the balanced equation for this reaction. So I'm going to do that. I'm going to say H2SO4 plus NaOH. Now, what's going to happen? An acid plus a base will give me a salt plus water. What salt am I going to deal with? Well, the salt, we always start with the metal, which is sodium in this case. Now, sodium has a valency of +1, and I want to link that with the sulfate, which comes from the acid. I need 2 of those. I'm writing down the formula for the salt, sodium sulfate, correctly. I'll come to balance the equation just now. Now, what else is there? There's water. Now, let's make sure that we've got this balanced. How many sodiums did I have on the left-hand side? Only 1. So I'm going to need to have 2 of those. Next thing I need to recognize, I've got 2 sodiums over there, 2 sodiums over there. I've got 1 sulfate, that seems fine. I've got 1 sulfate. Now, if I've got 2 oxygens, I'm going to need 2 oxygens on this side. So I'm going to put a 2 over there. That means I've got 2 times 2, which is 4 waters, 4 hydrogens in my water, 2 water molecules, 4 hydrogen ions, 2 hydrogens there, 2 hydrogens there, it's 4. It's balanced. Now, please take note of this. Balancing and checking your acid-base equations is extremely important. Because if you don't get the balanced equation correctly, then your ratios, particularly in titration calculations, are going to be off. You need to make sure that you've got the correct ratio of acid to base. You need to be able to work with the balancing coefficients. What does this tell us? That for every mole of sulfuric acid, I need 2 moles of sodium hydroxide to get me my neutral point. So I'm going to need to work with that. Now, there are all sorts of tricks and funny equations that you can use, and if you're being taught that, that's fine. I like to do these calculations from first principles, and I think it's a very important thing because it helps you understand exactly what's going on, to show you that you are using all of the substances that you've got here. I'm using all of that and all of that exactly matching. They're coupling off each other so that I'm only left with the material, the salt and water at the equivalence point. And we call it equivalence because it's not always exactly the same moles of acid added to the same moles of base. In this case, we recognize that we've got a diprotic acid. Hydrogen sulfate is diprotic. Sulfuric acid is diprotic. There are 2 hydrogen ions for every molecule. So we need to take that into account. So what information are we given? We're told, and it's important to pull this information from here. We've got an amount, that's a volume of acid. The volume of acid is 12,3 centimeters cubed. And it's a concentration of acid is equal to 0,03 mole per decimeter cubed. Okay, so I'm going to need to have that information. I'm going to pick that up and just move it down to my question where I'm going to need it, because that's the first bit of information that I need in my calculation. So I've got the information from the question for my acid. I've got the volume of the acid, and I've got the concentration of the acid which is given. The next thing, I'm told the volume of the base, the volume of the basic solution, 36,9 centimeters cubed. So let me write that down. The volume of the base is 36,9 centimeters cubed. Now, I hope you have got this very clear in your heads. We've taken things from the equation and we've taken things from the question. We now look at what we need to find. We need to find the concentration of the sodium hydroxide. We're wanting to find the concentration of the base. Okay, so how are we ever going to do this? Well, let's start with what we know. And the starting point for me is I know the concentration of the acid, I know the volume of the acid. I always try and work out the number of moles of things present. So I'm going to say I want to know the number of moles of acid. And I remember the formula that says concentration is equal to the number of moles of acid, concentration of acid, over the volume of the acid. So I rearrange that equation and I can see that I'm going to get concentration of the acid times the volume of the acid, and that will give me the number of moles of acid. So where am I? 0,03 multiplied, notice this was moles per decimeter cubed. I've been given centimeters cubed here. Now, please don't make a mistake. We can't work in centimeters cubed. We've got to change it to the SI unit for volume for this particular calculation, working out the number of moles of acid. So we've got to change it to decimeters cubed. How do we change from centimeters cubed to decimeters cubed? Now, centimeters cubed is like your milliliters, and decimeters cubed is like your liters. So you shouldn't get confused. A liter bottle has 1,000 milliliters. A decimeter has 1,000 centimeters. So we're going to divide the centimeters cubed by 1,000. So I'm going to write it just like that, but in exponential form. And I'm just going to say, let's divide by 1,000, which I'm writing as multiply by 10 to the minus 3, which is exactly the same thing. I'm now ready to work out the number of moles. So let me get my calculator up. And hopefully it will get up there. And there we go. So let's enter the figures on the calculator. We're going to say 0,03 multiplied by 12,3, and now we're going to do the divide by 1,000 times 10 to the minus 3, and we're going to get 3,69 times 10 to the minus 4. 3,69 times 10 to the minus 4. 3,69 times 10 to the minus 4. Now what's this? Moles of sulfuric acid. Please note that this is moles of sulfuric acid. Okay? It was the volume of sulfuric acid, it was the concentration of sulfuric acid. But here's the trick. We need to be very clear. What we're saying is for every 1 mole of this, we're going to need to neutralize 1 mole of that. It's diprotic. We're going to need to get twice as many moles because the ratio here is 1:2. Take a look at it. See, there's a 2, there's a 1. So for every one of those, there are 2 of those that we need. So the number of moles of base that is going to neutralize this, the number of moles of base is equal to twice the number of moles of acid. How did I get that? Because I see the ratio from the equation is 1 acid, 2 base. So I'm going to take that answer and I'm going to say the moles of base that I've got is not going to be that. It's not 1:1. The ratio is 1:2. I'm going to multiply it by 2. I'm going to get the answer which now tells me it's 7,38 times 10 to the minus 4. 7,38 times 10 to the minus 4. 7,38 times 10 to the minus 4 mole of sodium hydroxide. Remember, an acid-base reaction is one where the number of moles of hydrogen ions is going to be exactly equal to the number of moles of hydroxide ions. They need to pair off. But sulfuric acid, for every molecule of sulfuric acid, there are 2 hydrogen ions. So I need double the number of moles of sodium hydroxide, because sodium hydroxide can only contribute 1 hydroxide for every sodium hydroxide molecule. So that's what that is. So now, what else do I need? I need concentration of the base. And there's the formula that I'm going to use. It's just going to be changing the subscript. Concentration of the base is the number of moles of the base divided by the volume of the base. I've got the volume of the base. I've got the number of moles of the base. I've got that, so I can work it out. So 36,9 centimeters cubed is the volume. I want concentration. So concentration of the base is the number of moles of the base divided by the volume of the base. Well, we can just write it from there. 7,38 times 10 to the minus 4 divided by 36,9 centimeters. Can I leave it as centimeters? No. I must multiply or divide by 1,000. Multiply by 10 to the minus 3. I like working in scientific notation. I'm multiplying by 10 to the minus 3, which is the same as dividing by 1,000. So what does this give me on my calculator? Let's have a look. There's my 7,38 times 10 to the minus 4. I'm going to divide that whole answer by 36,9. And I'm going to say that must be exponent minus 3, because I'm dividing by 1,000. And here is my answer. It's 0,02. So the concentration of my base is 0,02 moles per decimeter cubed. Okay. Please note, the SI units are correct. If I hadn't worked with the correct volume, I wouldn't get the right answer. So please make sure, for accuracy and consistency, that you work properly, that you do the conversions. You're letting the examiner know, I know what the SI units are. Now, you might say to me, but in some cases, centimeters will cancel with centimeters and it will all work out fine. But you're not showing an understanding to the examiner. So here's the easy way of doing it. I think it's the easy way. It's the thinking way of doing it. If you just simply plug and play into some of the formula that you see in the textbook, you won't understand that very important concept of neutralization and of equivalence. Equivalence is telling us that for every acid, H plus, there is exactly one OH minus, and they've joined together. At the end of the result, the number of hydroxide ions is equal to the number of hydrogen ions, and in fact, they're equal to 1 times 10 to the minus 7, because we've neutralized. We've got a pH of 7 at the equivalence point. Okay, let's move on. Our next question deals with pH. And this is a really interesting idea, because we're going to apply the pH equation here. It says a certain species of fish cannot survive in water having pH less than 5,5. So fish can survive if it's bigger than 5,5, it's close to 7, they're fine. If it gets below 5,5, it's become too acidic. Remember, the lower numbers mean more acidic, higher numbers more alkali or basic. But that doesn't mean that the fish could survive at 14. Probably wouldn't be able to. It could survive around 7. Most fish are in that sort of concentration. It tells us in the river the hydrogen ion concentration was measured to be 3,2 times 10 to the minus 5 mole per decimeter cubed. Will the species of fish survive in the river? Show clearly how you arrived at your answer. So what they're telling you is the hydrogen ion concentration is equal to 3,2 times 10 to the minus 5. Now, please do not just guess here and say, pH, we know that the formula for pH is negative log of the hydrogen ion concentration, so we reckon that minus 5, it's all good. Now, you have got to use that value as well. You can't only look at the power. So you've got to use your calculator. So the steps on the calculator are extremely important. So what are we going to do? We're going to say we want the negative log. So I'm going to put negative, and I'm going to find the log, which is there. I'm now going to put in my equation 3,2, put in the exponent, minus 5, close my bracket, and there I filled it in, just like it showed me in the question. I'm now going to say I want to know what that answer is, because that's going to be my pH. And here my pH is given as 4,49. I'm going to round off to 2 decimal places, and I'm going to say, so my pH is equal to 4,49. Notice pH doesn't have any units. Just check my answer. It is correct, 4,49, and that's perfect. Now, have we answered the question? No, the question said, please note, will the species of fish survive? So what's our answer? We've done the calculation. I didn't substitute in entirely, but I did it on the working. What we recognize is we've got a lower pH. We need to recognize this is a lower pH. This is less than a pH of 5,5. So the fish, therefore, the fish will not survive. This river is too polluted. It's been my pleasure being with you. I wish you all the best for your study of acids and bases. Bye for now.